Hello. Today we're going to talk about the Bronsted-Lowry definitions of acid and bases, and we're also going to learn how to determine the conjugate acid-base pairs that are associated with this definition. Before we get started on that, let's think about what we've already learned. We know that pure water isn't really just a single thing. Pure water dissociates and breaks apart into ions. So here we have a water molecule, we have a hydrogen ion and a hydroxide ion. This happens over and over again. The arrow is going in both directions, meaning it's a reversible reaction. They're both happening at the same time. And it's a very small amount of hydrogen ions that are produced in pure water at any given time. You should have a concentration of hydrogen ions of about 1 times 10 to the negative 7th. In other words, 1/10,000,000th of a mole in every liter. So 1/10,000,000th of a mole, a very small amount. And that would give us a pH of 7 in neutral water. In reality, that hydrogen ion doesn't just hang out by itself. It associates with another water molecule, forming a hydronium ion. So the hydronium ion is just a water molecule with that extra hydrogen ion attached, and it's more correct to call it that, but it's simpler to talk about it as if it looks like this, so we often do. In the late 1890s, a man named Arrhenius came up with an explanation of what acids and bases were based on hydroxide ions and hydrogen ions. He said that an acid was a substance in water that would release hydrogen ions. So here I have hydrogen chloride, often called hydrochloric acid, because when it is in water, it dissociates, releasing hydrogen ions, which makes the concentration go way up, and it becomes a much lower pH. Sodium hydroxide, on the other hand, is a base. It releases hydroxide ions in water. So in water, it dissociates, and the sodium ions and the hydroxide ions are separated, and the amount of hydroxide ions increases significantly, making it a base. The problem with the Arrhenius definition is that it describes acid and base reactions in water. The Bronsted-Lowry explanation is not limited to aqueous solutions. So let's look at that. In the 1920s, two scientists named Bronsted and Lowry came up with a definition of acids and bases that, instead of talking about the hydrogen ions and hydroxide ions, talked about a proton donor and a proton acceptor. A Bronsted-Lowry acid is a proton donor. A Bronsted-Lowry base is a proton acceptor. So why are we talking about protons? We know that pH has something to do with acids and bases, and that pH has to do with the hydrogen ion concentration. Well, let's look at this here. This is the structure of a hydrogen atom. A hydrogen atom, you'll recall, has only one proton and one electron. There's usually no neutrons in a hydrogen atom. If it becomes an ion and it loses that electron, all that's left is a proton. So a hydrogen ion is a proton. You can use the terms interchangeably. All a hydrogen ion is a single proton. So let's look at some acid-base reactions from the Bronsted-Lowry definitions. Here we have a reaction. We have HCl, hydrogen chloride, and NH3. This hydrogen chloride will dissociate and give up a proton or a hydrogen ion to the NHCl. Since it is giving one away, to the NH3, since it is giving a proton, it is donating a proton, we call that an acid. And we call the NH3 a base because it's accepting it. Looking at the other side of the arrow, we can see that the HCl, after it has lost its hydrogen, just becomes a chlorine ion. The chlorine ion is a conjugate base. It's the acid after it's lost its hydrogen ion. The NH4 becomes the conjugate acid. It's the same molecule that we had here after it has gained a hydrogen ion. Notice we not only have an extra H here, we also have the positive charge. Let's do another one. Here we have PO4 with a -3 charge. Now, there's no protons for it to donate, but over here we have HNO3. This one has the extra hydrogen ion that it could donate. So this must be the proton donor. This is the acid. Over here, it could accept the hydrogen. That becomes the base. Now we have NO3-. It is this molecule after it has lost its hydrogen ion. So it must be the conjugate base. The conjugate base is the acid minus H and a positive charge. This here is the same as the original base, but it's gained a hydrogen and a positive charge. So this becomes the conjugate acid. Notice we have a reversible reaction. If the reaction was going in this direction, then this conjugate acid would give up that hydrogen to become that. It would be the donor. And this one would accept the hydrogen to become that. It would be the base. The conjugates are the acid and base of the reverse reactions. One more time. Which one has a hydrogen it could donate? This one here. There's where our hydrogen ion is going to come from. This is our hydrogen donor. Or our hydrogen ion donor, our proton donor. So that's our acid. And this one is going to accept the proton. And if it accepts the proton, then it is the base. The conjugate base is the acid after it's lost its hydrogen ion. That would be this molecule over here. And the conjugate acid is the base after it's gained the hydrogen ion. That's the conjugate acid. Can water be involved in Bronsted-Lowry acid-base reactions? Yes. So I have a couple reactions here that involve water. The first one, I have a sulfur ion and water reacting. Now, the sulfur ion can't be a proton donor because it doesn't have any hydrogen ions to give up. So the proton donor has to be the water. So in this case, we have water being the acid. The sulfur, on the other hand, accepts the hydrogen ion. It's a proton acceptor, so it's the base. That means the acid, after it's lost its hydrogen ion, becomes the conjugate base. And the sulfur, after it has gained its hydrogen ion, becomes the conjugate acid. Let's do another one. Down on the bottom here. This time, the HNO2 can give up a hydrogen. It has a hydrogen to give up, so it becomes the proton donor. And it is an acid. The water, in this case, accepts that hydrogen. It accepts the proton. It's the base. Over here, we have the acid after it's already lost its hydrogen ion. So it becomes the conjugate base. This here is the base with an extra hydrogen ion. It becomes the conjugate acid. Notice in these two examples that we have water in the first one being an acid and water in the second one being a base. Water can sometimes act as a Bronsted-Lowry acid and sometimes as a Bronsted-Lowry base. There's a special word for that. It's called amphoteric. An amphoteric, remember ampho, like amphibians, means both. Amphibians can live both on land and in water. They have both lives. Ampho means both. So amphoteric molecules are ones that can be both an acid or a base, depending on the reaction. That's all for today. Have a good week.